Hi, okay, so apologies for this morning with the technical issues. So I'll just go through some examples of the things that I want you to be able to do, and obviously refer you to the questions in the booklet for them. So the first one was being able to balance equations correctly. So, and if I recall correctly, they're on about page 2 to 6, just since I had to give out the last booklet there. So they've got plenty of questions in there along with the answers on the back that you are working through. So just to go through a couple here, just for those that were still struggling. So remember, you can only put numbers in the big areas in front. You cannot change these smaller numbers. If you do, you're changing the actual chemical itself. Right, so in terms of C2H6, that's basically 2 carbons and 4, 5, 6 hydrogens there. We've got 2 oxygens currently. We've got 2 hydrogens there with 1 oxygen, carbon, and 2 oxygens. You do not need to show kind of working out like this each and every time. It's more just, if it's your first time doing balancing equations in a long time, it will help. As you get better with it, you can probably just hold the numbers in your head and rearrange that way. So to start us off, I can see I've got 2 carbons on the left. So 2 here, none there. So my reactants and products, they need to be the same. Currently, I've only got 1 carbon across here. So what do I need to multiply 1 by so that it equals 2? So then they balance out. Well, obviously 1 times 2 equals 2. So I would put a big 2 in front of there. So what that now means is I now double everything here. So I've now got 2 carbons and 4 oxygens. So my carbons are now balanced. That's that done. Next, I'd have a look at the hydrogens. I've got 6 on this side. There's no hydrogens there. I've only got 2 on this side, none there. So what do I multiply 2 by to equal 6? 3. So big 3 in front of there. And again, that now means I'm writing water out 3 times essentially. Kind of like that. So I've got 6 hydrogens on that side and 6 on the right hand side. That's sorted. So carbons and hydrogens done. Last one's oxygen. Currently I've got 2 oxygens here. Across this side I've got 4, 5, 6, 7. Now, when it's just the diatomic, like oxygen, you can have fractions. Some people like to avoid them, so I'll show you that in a moment. But what do I multiply 2 by to get up to 7? 3.5. You can't have fractions of the diatomics, because what you're essentially saying is half of 2, so 1 there. But if you want to avoid that, what you can do instead, so rather than having 1, 3.5, 3, 2, you could have went 2, 7, 6, 4. And it still maintains the simplest whole number ratio that you're actually going for there. Now, next one. So I've got 2 borons, 6 bromines, 1, 2, 3, 4, 5, 6, hydrogen, nitrogen, 3 oxygens. I've got 1 boron there. Now the bracket means I've got 3 of everything in the bracket. So essentially I'm writing NO3 out 3 times. So I've got 3 nitrogens, 3 times 1, 3. And I've got 3 times 3, so 9 oxygens. and then H, Br there. So if we start with the borons, I've got 2 on this side, so I must have 2 on the other side. I've only got 1 currently, so I need to multiply this by 2. That now doubles everything I previously had. So I've now got 2 borons and 6 NO3s. But borons are now balanced. Bromines. I've got 6 on this side, I've only got 1 on this side. So I need to multiply by 6. So that I'm 4, 5, 6. 5, 6. So 6 bromines, 6 bromines, that's that sorted. Hydrogens. Now I've got 6 on the right hand side, I've only got 1 on the left hand side. So big 6 in front of there. And that means multiplying everything out a lot more. So I've essentially got, if I leave that as one of them, 1, 2, 3, 4, 5, 6. I'm running out of space a lot. 1 NO3, 2, 3, 4, 5, and there. So if I just shorten that down, so easier to see like that. So the hydrogens are sorted, 6 on the left, 6 on the right, that's fine. Now the next one, nitrogens, 1, 2, 3, 4, 5, 6 on the left, 1, 2, 3, 4, 5, 6 on the right. Nitrogens are fine. Now the oxygens, 3, 6, 9, 12, 15, 18 on the left, 3, 6, 9, 12, 15, 18 on the right. So the oxygens are sorted as well. So 1, 6, 2, 6 for balancing that equation. So those are probably as tough as you'll see in terms of multiplying everything inside the brackets. So that's the general methodology behind them. There are ways of speeding them up. You'll probably find them out on your own just as you go through practice with them. I.e., I could have just treated the NO3 as a lump, since the NO3 as a lump is on the right. 6 NO3s there, 6 NO3s here, and that ticks off nitrogen and oxygen at the same time, essentially. So there's little tricks like that, just for getting quicker once you've had a bit of practice. Now, the titration questions. Say titration in this case, it's what we're doing, but essentially it's just any reaction this applies to. So we could have had a solid reacting with a solution, for example. But the questions for these are on pages 26 to 27 of your booklet. So this one, if I remember right, let me just quickly check. Yeah, this one's number 5 from the booklet, just to go through it. And the methodology for pretty much all of them, up to 9. Yeah, 10's a little bit more difficult, but 4 through 9, the methodology for these is exactly the same. So if I can do one of them, you should be able to follow and complete the rest. Now, what's it asking us for? It's saying find the concentration of the sodium hydroxide in moles per decimeter cubed. So we'll look at this initially, and then we can just convert it to grams per decimeter cubed later. Now, what am I given in the question? Well, I'm given the volume of NaOH there. I'm given a volume H2SO4 here, and a concentration of H2SO4 there. But as we know, with N equals C times V. In order to work out the concentration of sodium hydroxide, I need the moles and the volume. So the way of doing this, right, if we set up a little table, we've got NaOH, H2SO4, and down the side, since they're both solutions, I can put moles, volume, and concentration. So you may need to alter this a little bit. Say if one of the sides was a solid and the other was a solution, you could have N equals CV down one side and moles mass MR down the other. But in our case, for all of these questions, we're just looking at the solutions. So I'm going to fill in what I actually know from the question first of all. So I know the volume. I need to convert that. So dividing by 1,000, remember, cm cubed, dm cubed, you divide by 1,000. So I've got 0.025 there, 0.0188 here for the sulfuric acid, and I've got the concentration of it there as well. Now, if I know the volume and the concentration of the sulfuric acid, using this equation, well, I can work out its number of moles. So if I just get my calculator here to do this, 0.05 times 0.0188, and that comes out as 9.4 times 10 to the minus 4. If I just annotate that, N equals C times V, 0.05 times 0.0188. Now, so the question is I still need moles across here in order to figure out the concentration. So I need to know this. How do I get that? Right, well, it says with this, since we're doing titrations, we go until neutralization has occurred. Now, this is why the balancing equation bit is important with it. We need to know this balanced equation. So it's given to us here, so that's nice. But usually you'd have to balance it yourself. And the key thing to pick out from it is we've got this 1 to 2 ratio. So what it means is every 1 mole of sulfuric acid will neutralize 2 moles of sodium hydroxide. So if I write that out, 1 mole so i.e., if I had 6 moles H2SO4, then I will neutralize 12 moles of sodium hydroxide. So the 1 to 2 ratio in there is maintained. Now I don't have 6 moles. I've got 9.4 times 10 to the minus 4, but the general ratio still holds the same, the 1 to 2. So whereas here we went from 6 to 12 because I doubled it, 1 mole will neutralize 2 moles. Then I go 9.4 times 10 to the minus 4 times 2, and that gives me 1.88 times 10 to the minus 3. Now from that, I now know the moles and the volume. So we know we can rearrange the equation and C equals N divided by V, so i.e. the 1.88 times 10 to the minus 3 divided by 0.025. And if I quickly do that, then we get an answer of 0.0752. That there is our concentration that it wanted us to work out in moles per decimeter cubed. Now, the other little bit that it asks is just to convert to grams per decimeter cubed. Now, with the unit grams per decimeter cubed, but sometimes used a bit more pharmacy-esque situations, we can see the volume is the same, the per decimeter cubed. I can basically ignore them. What I want to do is to convert moles to mass, essentially. So if we remember the equation, moles equals mass over mR. If I want to change to mass, mass equals moles times mR. So to change this moles bit here to mass, I'm just going to multiply by mR. So 0.0752 times mR of NOH is 40. And that gives me 3.008 grams per decimeter cubed. So that is that bit answered. Nice and easy for the second bit. So the key important bit with these questions is usually this moles bit in here. You need to make sure you get the ratio conversion right between them. So if you just practice the questions 4 through 9 on pages 27, if you're feeling very good, try question 10, and that's kind of much higher level.